In today's lecture, we are going to have another exercise of one-way ANOVA. And in this case, we are taking the example from fish. The otolith diameter of fish grown at different temperatures was measured. The nominal variable in this case are ponds with different temperature values, and these are samples or are treatments. And there are three categories of these treatments of different temperatures. The sample number 1 is from the treatment, which is 16 to 18 degrees Celsius. Sample number 2 is the treatment, which is 19 to 21 degrees Celsius. And sample number 3 constitutes the fish which are grown at the temperature treatment of 22 to 24 degrees Celsius, right? So we have three categories of the nominal variable over here. And the measurement variable is the otolith diameter. Now the question is there a difference in the mean otolith diameter of fish grown at different temperatures? The null hypothesis is the mean otolith diameter of fish grown at different temperatures is same. The alternate hypothesis is there is at least one significant difference in the mean otolith diameter of fish grown at different temperatures. You can also write this alternate hypothesis as that the mean otolith diameter of fish grown at different temperatures is different, right? But I have written this statement here to be more elaborate and to be more specific about the basic assumption of ANOVA, right? And these are the observations that we have, not the observations, but this is the descriptive statistics, right? So remember, what is the difference between observations and descriptive statistics? Observations is your raw data, your observations, the score of your observations, and this is the descriptive statistics that you work out from those observations, right? And this table of descriptive statistics is going to be used for the calculation of ANOVA during the ANOVA computation. So what do we have in this descriptive table is the total number of observations in each of the samples and then the grand total of the number of observations. So these are 50 in sample number 1, 45 in sample number 2, and 44 in sample number 3. So the total number of observations is 139. Then we have the mean otolith diameter in case of sample number 1. This is 9.017 millimeters. In sample number 2, this is 6.025 millimeters. And in sample number 3, this is 4.847 millimeters. The variance in sample number 1 is 13.27 millimeters. Variance in sample number 2 is 15.41 millimeters, and variance in sample number 3 is 23.08 millimeters. The summation x, which is the sum of all individual observations, for sample number 1 this is 450.84, for sample number 2 this is 271.13, for sample number 3 this is 213.26, and the total is 935.23. Then we have the square of summation x. So this is the square of 450.84 for sample number 1, and the answer is 203,255.8. And then we have the square of sample number 2, which is the square of 271.13, and we have the square value for sample number 3, which is the square of 213.26, and the answer is 45,480.24, right? So this is the situation that we have. And then in the last row we have summation x square, which is the square of individual observations, and then we take their sum. For sample number 1 this is 4,715.2, for sample number 2 this is 2,311.75, and for sample number 3 this is 2026.02, and the total is 9052.97, right? So this is the situation that we have here in the descriptive statistics. Now step 1 is to make a table of descriptive statistics that we have already done. The step number 2 is test for homogeneity of variance. Remember, before computation of ANOVA we have to check that whether population variances are same or no. And we do it by a simple Fmax test, and the Fmax test is largest variance divided by smallest variance. The largest variance in this example is 23.08 and the smallest variance is 13.27 and the ratio is 1.74. So let's see that whether this ratio is significant or no, and for that purpose we need the A value, which is the number of samples or treatments, which in this case is 3, and the degree of freedom of every sample or the smallest sample. So in this case we have different sample sizes, so the degree of freedom that we are going to choose for the Fmax test is the degree of freedom of the smallest sample, and the smallest sample is 44, right? The number of observations in the smallest sample is 44, so our degree of freedom is going to be 43. So here we are with the values. So the table value 1.94 at A of 3 and degree of freedom 43. So variances are homogeneous. We can proceed with ANOVA. Now in the step number 3 we have to calculate the correction term, right? And remember the formula for correction term. This is the summation xt whole square divided by nt. So 935.23 square divided by 139. So we have here 6,292.4831. Now step number 4 is we have to calculate total sum of squares, and the formula for that one is summation x square minus correction term. So this is 905.2.97 minus 6292.4831, and the answer is 2760.4869. so this is our total sum of squares. Then we have to calculate the sum of squares between samples, and we have 3 samples, so we have the values for each of the samples, and then we are going to subtract them from the correction term, right? So the values for the first sample are 203,255.8 divided by 50, and the values for the sample number 2 is 73,512.64 divided by 45, and the values for sample number 3 is 45,480.24 divided by 44. Then we take the sum of these values and subtract them from the correction term, and here we are with the sum of squares between, which is 439.89, right? Now our step number 6, which is the calculation of sum of squares within. So in that case we have to calculate the individual sum of square values. So sum of squares for sample number 1 is the summation x square minus summation x whole square divided by n1. So in this case we have the values 4715.2 minus, we have the product of 203,255.8, which is 203,255.8 divided by the number of observations in sample number 1, which is 50, and the answer that we get is 650.084. So this is the sum of squares for sample number 1. Then we have sum of squares for sample number 2, and for that purpose we have summation x square, which is 2311.75, and then the summation x2 whole square is 73,512.64, and this is divided by the number of observations in sample number 5, which is 45, and our answer is 678.136, which is the sum of squares for sample number 2. Then we have the sample number 3, and the summation x square for sample number 3 is 2026.02, and the summation x3 whole square is 45,480.24, and this is to be divided by the number of observations in sample number 3, which is 44. So we get the answer, which is 992.378, which is the sum of squares for sample number 3. Now remember the next step that we have. The next step is to take the sum of these individual sum of squares, and that will be our within sample sum of squares. So 650.084 plus 678.136 plus 992.378, and the answer is 2320.598. So this is the value of our sum of squares within. Now we can cross-check these values, and this is because the total variability is equal to between variability and within samples variability, and so is the case with the sum of squares, that the total sum of squares is equal to the sum of squares between and sum of squares within. So if we want to work out any of these values, we need to have the information about two other values. So in this case, we want to cross-check the value of sum of squares within. So for that purpose, it is total sum of squares minus between sum of squares. So the total sum of squares that we calculated is 2760.4869, and the between sum of squares that we calculated was 439.89. So their difference is 2320.598, and this confirms that our calculation of the individual sum of squares and then taking their sum for the sum of squares within is correct, right? Now the next step is to determine the number of degrees of freedom for each sum of squares. So degree of freedom for the total sum of squares is the total number of observations minus 1. So what is our total number of observations? This is 50 plus 45 plus 44, which is 139. So 139 minus 1 is 138. So this is the degree of freedom for the total sum of squares. And then degree of freedom for the between sum of squares, and this is A minus 1. So remember, A is the number of samples or the number of treatments, which in this case we have 3. So 3 minus 1 is 2. So 2 is the degree of freedom for between sum of squares. Then we have degree of freedom for within sum of squares, and for that purpose we have to take the total number of observations minus the total number of samples. So the total number of observations are 139, and the number of samples or the number of treatments that we have, these are 3. So 139 minus 3 is 136. So we can do this calculation for the degree of freedom for sum of squares within in another way too. And what is the other way? That we calculate the individual degrees of freedom for each sample and then we take their sum. So this is going to be the same value, right? Now we have calculated their degrees of freedom. So what should be the next step? So remember, in the ANOVA results table, what do we have? We have different columns. The first column is for the sum of squares, the second column is for the degrees of freedom. So we are done with these two calculations. What is the next column about? The next column is for the calculation of the mean sum of squares or the variances, and we calculate two variances: the variances between samples, between treatments, and the variances within samples, right? So we are going to calculate variances now. So here we are for the calculation of variances. So the first variance that we are going to calculate is the variance between samples. So for that purpose, we are going to divide the sum of squares between by the degrees of freedom between. And the answer is 439.89 divided by 2, 219.945. So this is our variance for between samples variability. Then we have to calculate the next variance, which is the variance within, and for that purpose we are going to divide the sum of squares within by the degrees of freedom within, which in this case is 2320.5969 divided by 136, and the variance within is 17.0632, right? So here you can see that between variance is greater than within variance. Now what is the next step in the ANOVA computation? The next step is to calculate the ratio of between and within variances, right? Which is the value of our F in ANOVA. So next step is to compute the value of F for ANOVA, and F in this case is obtained by dividing the between samples variance by within samples variance, right? So between samples variance divided by within samples variance, and which in this case is 219.945, which is the between samples variance, which is greater, and it is divided by 17.0632, which is the within samples variance, and the answer is 12.89. Now, the thing is that if our within samples variance is greater, are we going to take within samples variance as numerator? No, this is not the case, because this f-test is one-tailed. So within sum of squares always has to be the denominator. It cannot be taken as numerator. Whether it is small or it is greater than between samples variance, it has to be taken as the denominator, right? So here we are with the f value, which is 12.89. So what is the assumption of ANOVA? The assumption of ANOVA, or the null hypothesis of ANOVA, is the population variances and population means are similar. And we already checked that population variances are similar through the Fmax test. So now we are checking that whether their means are different or no, and for that purpose we have to compare the between samples variance and the within samples variance. So in this case, according to our null hypothesis, if the population means are similar, then the ratio of between samples variance to within samples variance should be equal to 1. So they should be same, right? But in this case, what do we see here is that the ratio is greater than 1. So this ratio is 12.89. Now, how we can confirm that this ratio is significantly greater than 1 or no? For that purpose, we have to compare the calculated f value with the tabled f value, right? So tabled values are 3.06 at probability of 0.05 and 4.76 at probability of 0.01 and 0.001 at 7.27 at probability of 0.001. And remember, what is our calculated value? Our calculated value is 12.89, which is greater than the calculated table value at probability 0.05, which is 3.06. So we reject our null hypothesis. Then we see that whether our result is significant at the next level of significance or no. So we see that it is significant. It is highly significant because the calculated value is greater than the table value of 4.76. Then we jump on to the next level, which is the probability of 0.001, and we see that our calculated value is greater than the table value, which is 7.27 at probability of 0.001. So we can say that our result is very highly significant. So now we are going to state the result, and the result is the difference in the mean otolith diameter of fish grown at different temperatures is very highly significant, right? So the f value is 12.89 and probability is less than 0.001. Now remember, whenever we state the results of ANOVA, we have to state the f value, and the f value is stated along with information about the degree of freedom against which we have taken that f value. So the degree of freedom in this case is 2 for between and 136 for within. So these degrees of freedom, they are mentioned along with the value of f whenever we are reporting the results of ANOVA. So this is another exercise that we have done for the calculation of ANOVA, and this is the calculation of the simplest form of ANOVA, which is the one-way ANOVA, in which we have one nominal variable and one measurement variable. And the nominal variable in this case was different temperature treatments. So we had three different temperature treatments, and the measurement variable was the otolith diameter of fish, which was our response variable. And we saw the effect of different temperatures on the otolith diameter, and here is the result that we can see that there is a significant effect, very highly significant effect of temperature in which fish are grown on their otolith diameter. In this section, we are going to see that how ANOVA computation can be done on Microsoft Excel, and for that purpose we are going to take the example of the mean masses of starlings sampled from 4 different roosting places. So this is the same example that we solved during the exercise of one-way ANOVA. So we are going to use the same example here, and we see that whether the results are going to be the same or no, right? So in this case, the nominal variable is the roosting places, right? And which are also known as the samples. So there are 4 categories in the nominal variable. Nominal variable is only one, right? The nominal variable is the roosting places. And there are 4 categories or 4 samples into the nominal variable, which are different roosting places. This is red beet, tree, large building with leisures, and cliff, right? So this is our nominal variable. And what is our measurement variable? It is the mass, right? Mass of starlings is our measurement or our response variable. These are the observations that we have, and these are 10 observations from each of the samples. So total number of observations are 40. The question is there any difference in mean masses of starlings between different roosting places? And how we are going to proceed further, we are going to state the null hypothesis to answer this question. And the null hypothesis is there is no difference in the mean mass of starlings between different roosting places. And the alternate hypothesis is the mean mass of starlings of at least one roosting place is significantly different. We can also say that the mean mass of starlings of different roosting places are significantly different, right? So that's how we can state our alternative hypothesis in another way as well. So starting with the Excel workbook, so you have to open up your Excel workbook and you have to put your observations into Excel. So these observations, they are put into the columns, right? The observations are presented in columns according to samples. Now what we have to do next is we have to press the data analysis function tab. So here we have a pop-up window, and this window shows all the statistical tests that can be performed under the data analysis function tab of Microsoft Excel. And we have to find out the test that we want to perform. And because this is ANOVA, so this is the first test that is mentioned into this list. So we can see that there are 3 types of ANOVA that are mentioned here. The ANOVA for the single factor, ANOVA for 2-factor with replication, and ANOVA 2-factor without replication. So what type of ANOVA are we talking about? Are we talking about a single factor ANOVA or the 2-factor ANOVA? We are talking about the single factor ANOVA because the nominal variable is only 1, right? So we are going to select our desired test, which is ANOVA for the single factor in this case. We press OK, or we can double click the name of the test, and we will have another window popped up. So this window is for the input of your values and input of your test conditions. So here you can see that this is the box for the input of ranges. So what is the input range? These are the observations in your 4 samples. And then you can see that there is an option that the values are, or the samples, they are arranged or they are grouped by columns or by rows. So you have a flexibility here. So here I have arranged the observations in columns, but you can arrange the observations into rows as well, and then you press the option rows. So by default into this window, the option of columns is pressed. But if this is not the case, if your observations are listed as rows, that your samples are presented in rows instead of columns, then you can press the other option of rows. Then we have the alpha level, which is the level of significance that we are going to use. So the minimum level of significance that we should use is 0.05, and by default this one is mentioned here, right? So this is our alpha level. And then we have the output options. So these are the options for the output range. Now the first step is that we have to select the observations, and for that purpose we have to place our cursor into the input range, and then we have to select the observations, right? Now in the next step we have to select the output range, that where do we want to have our output. We want to have our output into the cell of the same sheet, or into a new worksheet, or into a new workbook, right? So we have these three options here. Now we want to have our output into the same sheet, and for that purpose we have to place the cursor here for the cell, for the selection of cell, and this is the cell that we select. And here is the output. So we press OK and we get the output. So when we expand the output, the columns of the output, we can see that we are given two tables, right? The first table is about the summary of descriptive statistics, and the other table is about the ANOVA results. So here you can see that in the summary table, the groups are given column 1, 2, 3, and 4, and the count, which is the number of observations in each of these columns, which was same in this case, and then the sum of observations is given. So this is 836, which is summation x1, then 794, which is summation x2, and 786, which is summation x3, and then 754, which is summation x4. Then are the mean values of the individual columns. So this is 83.6 for the sample number 1, 79.4 for sample number 2, 78.6 for sample number 3, and 75.4 for sample number 4. Then we have the individual variances. So individual variances are 16.2667 for sample number 1, 6.2667 for sample number 2, 10.933 for sample number 3, and 17.1556 for sample number 4. So this is the descriptive statistics. This is the summary of the observations that we have. Then is the result table of ANOVA. So the source of variation are between groups and within groups and the total, right? And the total variability is the sum of between samples variability and within samples variability. So the between groups variability, the sum of squares for in this case is 341.9. The sum of squares within in this case is 455.6. The sum of squares total is 797.5, which is actually the sum of these two. And then the degree of freedom for between groups is 3, right? Why it is 3 here? Because the total number of groups are 4, so degree of freedom is a minus 4. A is the number of groups that we have, or the number of samples that we have. So in this case we have 4, so this is 3. And then the degree of freedom 36. And how this within groups degree of freedom calculated, right? So this within groups degree of freedom is calculated by subtracting the number of samples by the total number of observations. So the total number of observations are 40 and the number of samples are 4, so 40 minus 4 is 36. And what is the total degree of freedom? This is the total number of observations minus 1. So this is the degree of observations for the whole experiment. Then we have the MS, which is the mean sum of squares, which is actually the variance. So between groups variance is 113.9667 and between groups variance is 12.6556. Then we have the F value, which is the variance ratio, which is the ratio of between groups and within groups variance. And this is 9.005268. Then we have the P value. So this is the direct P value that we have. So we don't have to compare the calculated F value with the tabled F value in this case. And we directly have the P value, and we can see that this P value is 0.000139, which is less than 0.05. It is also less than 0.01, and it is also less than 0.001. So our result seems to be very highly significant. And the critical value of F is also given, which is 2.87 at the probability level of 0.05, because remember in the input window we had selected the alpha level of 0.05, but you can select 0.01 or 0.001 as well. So here we have the result output when we compute ANOVA on Microsoft Excel, and you can see that this is the same result or no. Let's compare it. So these are the same results as we calculated on paper, right? So this is the table that I copied from the exercise when we solved it on paper. So this is the same values. a null hypothesis is rejected, and the result is the difference in mean mass of starlings from 4 different roosting places is very highly significant. So this is how we can do the ANOVA computation on Microsoft Excel, and you can see that once you have understood the concepts behind ANOVA, the computation of ANOVA is no big deal, right? There are many people who are confused by the ANOVA or who are scared of doing ANOVA, but ANOVA is nothing if you have your proper research design, if you have proper experimental design, and if you know the concept. Therefore, this course is important because it gives you the concepts for using different types of tests under different situations. So Microsoft Excel is there. Anyone can do the test over there, but unless and until you know that what are your inputs going to be and how do you interpret your output. So unless and until you have this information, this software or any other software is of no use. So that is why you need to have the basic information of statistics. So this is all for today's lecture, and see you in the next one.